So good afternoon everyone. In the previous class we have discussed single error correcting Hamming code. So in single error correcting Hamming code, the code length n has to be less than equal to 2 raised to n minus k of minus 1, and by trial and error method we determined n value and then we constructed H transpose matrix. And we have gone through table lookup decoding using standard array, the procedure and the steps to construct a standard array table for a n comma k linear block code. So in this class we'll solve a numerical on standard array table. Using this standard array table, we need to detect a transmission error occurred in the received vector. So there is a procedure to be followed in order to decode the error and to correct the error. So we'll solve the first few initial steps and then we'll come back to this procedure. So the problem statement is as follows. Construct the standard array table for a 6,3 linear block code. The parity matrix P is given by, so the first row is 101, 011 and the last row is 110. So for a 6,3 linear block code, we need to construct a standard array table for which the parity matrix is given. So the given linear block code is 6,3, where 6 represents n value and 3 represents k value. So n value is 6, k value is 3. K value represents each message length. So each message is of 3 bit. So we'll have 2 raised to k message vectors, that is 2 raised to 3 equals to 8 message vectors. Each message is of 3 bits and we have totally 8 messages. So now we need to compute the code vectors. So we had solved such examples in the previous class. But in this example, apart from code vectors, we need to construct a standard array table. So in order to determine code vector, the formula is matrix C equals to matrix D into matrix G. Where matrix D is the message matrix, or you can say it as input matrix, and G is the generator matrix. And the generator matrix is given by identity matrix of order K followed by a parity matrix. K value is 3. So identity matrix is of order 3 cross 3 followed by parity matrix. So write down an identity matrix of 3 cross 3. So 100, 010, 001. In identity matrix, all the diagonal elements will be 1. So this is identity matrix of order 3 cross 3 followed by, write down the parity matrix. So this is nothing but the G matrix, generator matrix. So now multiply generator matrix with D matrix. So since K value is 3, we have 3 bits in the message matrix, that is D. Since value of K is 3, we have 3 bits in matrix D, D1, D2 and D3. So now multiply D matrix with G matrix. So if I multiply this D matrix, that is row matrix, with the first column of G matrix, I'll be getting D1. Similarly, if I multiply D matrix with the second column of G2 matrix, I'll get D2. Similarly, if I multiply D matrix with the third column, the actual matrix multiplication is as follows. So D1 is multiplied with 0 plus D2 is multiplied with 0 plus D3 is multiplied with 1. So which will give us the final result as D3. So in turn, to make it easy or to write down the matrix multiplication result sooner, so this entire first row will be multiplied by D1 and the entire second row elements will be multiplied by D2 and the last row will be multiplied by D3. So if you consider the fourth column, D1 is 1, D3 is 1. Therefore, the fourth element in C matrix is D1 plus D3. Similarly, if you consider the fifth column, D2 is 1, D3 is 1. So I'll have D2 plus D3. Considering last column, D1 and D2 are 1. Therefore, we'll have D1 plus D2. So we have all the code vector elements. Since n value is 6, the code vector is of 6 bit. So it has C1, C2, C3, C4, C5 and C6 bits. So if you observe the code vector matrix, that is C matrix, C1, C2, C3 are nothing but the first 3 message bits. So in a n bit code vector, the initial few bits are nothing but message bits and later on we place check bits and the check bits are derived from the message bits itself. So the first 3 bits of code vector are message bits. So C1, C2 and C3 are nothing but the message bits. So this represents D1 message bit, this is D2 and the last one is D3. So C1, C2, C3 are same as these message bits. So coming to C4, C4 is XOR of D1 and D3. Perform D1 and D3 XOR, whatever result you get, that is C4th bit. D1, D3 XOR will give us 1, therefore C4 bit is 1. So C4 is computed by performing XOR of D1 and D3 bit. Similarly, if we perform XOR of D2 and D3, we'll get C5 bit, the 5th bit of code vector. D2 and D3, 1, 0, XOR 1, therefore C5 bit is 1. 1, 1, XOR is 0, so C5 bit is 0. Similarly, in order to get C6th bit, perform XOR of D1 and D2. This will generate you the C6 bit, 6th bit of code vector, the last column. So in order to construct the standard array table for any linear block code, first we need to determine the code vectors. For any linear block code, in order to construct standard array table, we need code vector. Standard array table is like an data sheet. By referring data sheet, suppose if you consider any IC, you can know what is the maximum voltage the IC can withstand or what is the minimum voltage required for that IC. So similarly here standard array table will act as a data sheet. By referring this table, we can detect and correct the error in received vector. So all these code vectors will form the first row in standard array table. So all the code vectors which we computed will form the first row in standard array table. So you can observe the first one is 0 0 6 zeros 6 0. Next 0 0 1 1 1 0. Similarly, third one is placed here. 0 1 1 1 0 1 is placed here. Similarly, the next four code vectors are placed. So all these code vectors will form the first row in standard array table. So in this table, the first column is a syndrome. As you know, syndrome is nothing but R into H transpose. So in this syndrome column, the first value is always 0. So we had gone through the procedure of standard array table. The first element is always 0. So even the syndrome has to be 0. Syndrome is of 3-bit because n minus k is of 3-bit. The length of syndrome is n minus k bit. The length of syndrome is n minus k bits. So each syndrome is of 3-bit. So the first value in the syndrome column is 0. And even the first row for coset leader is also 0. So in the syndrome column, next we place parity matrix and then the identity matrix elements. Nothing but we need to write down the H transpose matrix. Whatever elements are present in H transpose, the same thing will be part of syndrome column. So since we have not computed H transpose here, so we can rewrite here H transpose is nothing but parity followed by identity in minus k. So we know the elements of parity matrix 1 0 1 0 1 1 1 1 0 and then the identity matrix. So n value is 6, k value is 3, identity matrix is of order 3 cross 3. So the elements will be 1 0 0 0 1 0 and 0 0 1. So same H transpose matrix will be a syndrome here. You can observe here 1 0 1 0 1 1 1 1 0 and then the identity matrix 1 0 0 0 1 0 0 0 1. So this 1 1 will not exist. So this is how we fill this syndrome column. Syndrome column is nothing but the H transpose matrix. But before you write down H transpose matrix, the first element has to be all 0 element. So now coming to the other rows of standard array table. How to fill the other rows? So we'll start with 101 syndrome. So this second row is written by referring to the first row. Even third row is written by referring to first row. all the rows in the table are filled by referring to the first row. That is, the first row will act as an reference. So the first row in the table will act as a reference row. So now how to write the second column? So for the second column, from left to right direction, we'll assume the first bit is at error. In the next row, we'll assume second bit is at error, and then we'll assume third bit is at error, and then fourth bit is at error, and then fifth bit is at error, and sixth bit is at error. We know that n value is 6. So these cosets are also of 6 bit. So let me repeat how we filled this syndrome. Syndrome is nothing but the elements of H transpose matrix are written over here. But the first element has to be 0 and then the H transpose elements. And the first row of the standard array table is nothing but all the code vectors. So this coset leader is nothing but 1 bit error. So starting, we have 6 bits totally. So second row has a 1 bit error, first bit. Next row is at second bit error. Next row we have error at third bit. Next row we have error at fourth bit, and then error at fifth bit, error at sixth bit. The presence of error is represented by a binary 1. We have represented this by 1, so it represents there is an error at this bit. Similarly, there is error at this bit. The presence of error is represented by 1 at that position. So we have 6 bit code vector. Therefore, we have a 6 bit coset leaders too. And how this coset leader is written? We consider error at every bit. So that we cover all the 6 bit positions. So first, after reference row, we consider the first bit is at error, and then in the next row, second bit is at error, next row, third bit is at error, and then fourth bit is at error, fifth bit is at error, and sixth bit is at error. Where you have considered error, there you need to represent it by 1 and all the other elements will be 0. So presence of error is represented by 1 and all other elements will remain 0. So coming to the other elements of second row. So how these values are written? So we know that in second error, first bit is at error. So let me write it as 1. In the next row, second bit is at error. Next row, third bit is at error. Fourth bit is at error. Fifth bit is at error and sixth bit is at error. So if you recall the numericals covered in the previous class, if there was an error in a received vector, suppose received vector is 110. If there is error at this bit position, in order to correct it, we'll change it to 1. Fine. So similarly, if there is a 1 bit error, we'll change that bit to its opposite value. So this first row, reference row is nothing but the same code vectors we have computed. They will represent the first row. And syndrome, the first element is completely 0, and then we write down the H transpose matrix. And the coset leader column. how it is written. So coset leader is also of 6 bit because code vector is of 6 bit. So first assume the first bit is at error and then the second bit, third bit is at error, fourth bit is at error, fifth bit is at error and sixth bit is at error. So now coming to how the remaining elements are written. So as I said, all these rows are filled considering the first row as reference row. All the remaining columns are filled by considering the reference row. So first bit is at error. So change this 0 to 1 now. First bit is at error. So change 0 to 1. First bit is at error. We have 0 here. Change it to 1. First bit is at error. We have 1 here. So change it to 0. First bit is at error. Change it to 0. Again in the next column, first bit is 1. We have error. So change it to 0. In the next column, again, first bit is 1. We have error. So change it to 0. Only the first bit will be modified, all other bits will remain same. And how the first bit is modified? If you have 0, just replace it with 1. If you have 1, replace it with 0. This is how this first row will be filled. The reference. So we'll consider the first row as a reference row and then we'll label this as first row, second row, third row, fourth row, fifth row and sixth row. So it will be easy to explain. So now we'll go through third row. I mean this second row, how this second row is written. So how this row is written. Again, this row is also written by considering the reference row. But now the only change is instead of first bit, now second bit is at error. The second bit is 0 in the reference row. So this will change to 1. Second bit is 0. So it will change to 1. Second bit is 1. So this will change to 0. Second bit is 1. So this will change to 0. Second bit is 0. This will change to 1. We have 0 in the second bit. Change it to 1. We have 1. Change it to 0. Column we have change it. All other name will be same. Only the second bit will change now. In the next row, the third bit will be modified. Third bit is 1. In the reference row, change it to 0. Third bit is 0 in the reference row, change it to 1. Third bit is 1. Now it will change it to 0. Third bit is 0. It will change to 1. Third bit is 1. This will change to 0. Third bit is 0. This will change to 1. Third bit is 1. This will change to 0. So in this row, only third bit will change and all other bits will remain same. Similarly, in the next row, only fourth bit will be modified. Whatever fourth bit you have in the reference row, write down its opposite value. If you have 0 in the reference row, write it as 1. If you have 1, write it as 0. So we'll consider the last row. In the last row, sixth bit is at error. Sixth bit is 0. This will change to 1. Sixth bit is 1. So this will change to 0. Sixth bit is 1. Hence it will change to 0. Sixth bit is at 1. This will change to 6 is at 1. This will change to 0. Sixth bit is at 0, hence it will change to 1. Sixth bit is at 0, hence it will change to 1. So this is how you will construct this standard array table. And this table represents a standard array for 6,3 linear block code. So now, how this table is used in order to detect the error and correct the error in the received vector. Assume the received vector is 100,100. There are two procedures in order to detect and correct the error using standard array table. First, we'll go through the first procedure and then we'll understand the second procedure. So what is the given received vector? 100, 100. This is the given received vector. In this received vector, we need to determine what is the error and what is the corrected vector. So now the question is how this table is used in order to detect the transmission error in this received vector. So the given received vector is 100, 100. Check where this is appearing in this standard array table. So I have just marked it here. 100, 100 is placed at this position in the standard array table. So 100, 100 is appearing in sixth column and the seventh row. The received vector, given received vector 100, 100 is appearing in sixth column, seventh row. Fine. So wherever the given received vector is appearing, its topmost element will act as corrected received vector. So let me repeat, the given received vector is 100, 100. So our next step is to determine the error in this received vector. And once we determine the error, we need to correct that error. And error detection and correction has to be done using standard array table. In the previous class, we have detected and corrected the error using syndrome. We used to compute syndrome and then we need to check where this syndrome is lying in H transpose matrix. And then we used to detect the error and correct it. So, but now we have to use this standard. So what is to be done next? Check where this received vector is placed in the standard array table. So 100, 100. Received vector is placed at this position. The given received vector is appearing in the sixth column and seventh row. So once you identify the received vector, you can just mark it. So above this received vector, the topmost element, this is the topmost element, the first element. So this element will act as corrected vector. So given received vector is 1 0 0 1 0 0. This is appearing at this position. So in the same column, the topmost element will act as corrected vector. So what is my corrected vector? 1 0 0 1 0 1 is the corrected received vector, corrected R. Fine. So check where the given received vector is lying in the standard array table. So this is where the given received vector is lying. Where the given received vector is lying in the same column, the topmost element will act as the corrected vector. So my corrected vector is 1 0 0 1 0 1. So it means error is at 6th bit. In received vector we have 0, but in corrected vector I have 1. It represents 6th bit is at error. Or what we did in the previous class, same method can be applied. But we do not use a standard array table here. For any received pattern, by referring this table, immediately we can determine the corrected vector. But if we use R into H transpose concept, for every received vector, we need to compute the syndrome and then detect and correct error. 1 0 0 1 0 0 is the given received vector. Multiply with H transpose matrix. I'll obtain syndrome as 0 0 1. 0 0 1 is appearing in the 6th row of H transpose matrix. It represents 6th bit is at error. So 1 0 0 1 0, 6th bit is at error. I have 0, so the correction will have 1. So this is how you can detect and correct the error. Similarly, if I consider 4011, so let us decode this using standard array table. Check where this element is lying. 4011. So 4011. The second received vector RB. Second received vector is 4011. 4011. So is appearing at this position. Fourth row, fourth column, third row. This is where the received vector RB is placed in the standard array table. So in the same column, check what is the topmost element. So this topmost element is the corrected vector for this received vector RB. So what is the corrected vector? 0 1 0 0 1 1. 0 1 0 0 1 1 is the corrected vector. This was the vector sent. This was the vector received. So error is at second bit. Actually, we had sent 0 1 0 0 1 1, but we have received as 4 0 1 1. So second bit is at error. So this is how for a received vector we can determine and correct the error using standard array table. Let us verify it using R into H transpose concept. Substitute received vector. 4011 and substitute H transpose, multiply both R and H transpose, I get syndrome as 011. So 011 is placed in the second row of H transpose matrix. So it represents second bit in the received vector is at error. And how do I correct it? I have 0 here, so the correction will be 1. So this is the corrected vector. So let us consider one more case. Assume the received vector is 110100. So you need to detect and correct the error. So identify where this received vector is placed in standard array table. 110100 is placed at this position. So this is my received vector. So the topmost element is the corrected vector for RC. What is the corrected vector? 110110. So error is at 5th bit. Received is 0, but transmitted was 1 here at 5th bit. Whatever received vector is given, check where that is placed in the standard array table. Once you find where it is placed, in the same column, the topmost element will be the corrected vector. So this was my RC, the topmost element. This is the corrected vector for RC. This was RA, the received vector A. The topmost element is the corrected vector. Similarly, this was received vector RB. The topmost element is the corrected vector for RB. So this is how standard table can be utilized in order to detect and correct the transmission error in received vector. Similarly, one more example has been solved for a 7,4 linear block code and the parity matrix is given. So same thing has to be done here. So n value is 7, k value is 4. Compute the code vectors. How do we compute code vectors? D matrix into G matrix. What is a G matrix? Identity matrix followed by parity. Parity is given in the problem statement. Identity matrix is of order k. K value is 4. So write down identity matrix, substitute parity matrix. So this is nothing but generator matrix G. Multiply G matrix with D matrix. What is D matrix? Since k value is 4, D matrix has 4 elements, D1, D2, D3 and D4. So this is the C matrix. So if we multiply D into G, what are the elements of C matrix? So first column only D1 is 1. So C1 is D1. Next only D2 is 1. C2 is D2. C3 is D3. C4 is D4. Next we have D1, D2 and D3 1. So C5 is D1 plus D2 plus D3. What is C6? D1, D2 D4, D1, D2 and D4. What is the last element? D1, D3 and D4 are 1. So D1 plus D3 plus D4. So if you observe C matrix, the first 4 bits are message bits only. So the first 4 bits are message bits. C1 to C4 are nothing but D1, D2, D3, D4 message bits, and then compute C5, C6, C7. How do you compute C5? XOR D1, D2, D3. How do you compute C6? D1, D2, D4. D1, D2, D4. D1, D2, D4. XOR them. You'll get C6 bit. How do you get C7? XOR D1, D3, D4. D1, D3, D4 XOR will give a C7 bit. Same way, compute the code vectors for all the 16 messages. K value is 4, so 2 raised to 4, 16 messages, hence 16 unique code vectors. So now in order to construct standard array table for 7,4, we need to write down H transpose. H transpose is nothing but parity matrix followed by identity. Parity matrix is given. Same thing is written here again, followed by identity matrix. So the first column is syndrome. So the first element in the syndrome is 000, followed by H transpose matrix. And the first element of coset leader is all zeros. All these code vectors, 16 code vectors, will form the first row. So in this table, all the code vectors are not listed. Few of them are skipped. Hence, we have represented a dotted line. The first row is all the code vectors. Starting from 0, 0, 0, 7 zeros to 7 ones. All those code vectors will form the first row. Fine. Since n value is 7, code vector is of 7 bit. Hence, coset leaders are also of 7 bit. So in the second column, we assume here first bit is at error and then second bit is at error. And then third bit is at error. Next row, fourth bit is at error. And then fifth bit is at error. In the next row, sixth bit is at error and then seventh bit is at error. So this is how you fill the second column. So the remaining elements of second column are filled by just modifying the first bit. In the reference, only the first bit will be modified in order to fill the first row. First bit is 0, change it to 1. 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 First bit is 1, change it to 0. Similarly, the next row is filled by modifying only second bit. In reference row, second bit is 0. Second bit is 0, change it to 1. second bit is 0, change into 1. Second bit is 0, change into 1. Second bit is 0, change into 1. Second bit is 1, change into 0. Similarly, in the next row, only modify third bit. Then in the next row, only fourth bit is modified. And then only fifth bit is modified. Only sixth bit is modified. And then only seventh bit. The remaining bits will remain as it is. So this is how we construct standard array table. And in the previous example, we have seen how this table can be utilized in order to correct the transmission error in the received vector. So now let us construct the decoding circuit. So we have already constructed the encoding circuit. Encoding is used to add the check bits. Decoding circuit makes use of these check bits in order to detect the error and then correct the error, so that we can get back the original information that is transmitted. So we know that this error vector is a function of syndrome bits. So this is the general decoding circuit for n, k linear block code. We'll start with the received vector and then we draw the syndrome calculation circuit, error pattern detecting circuit, and finally we attain corrected output. Let us construct this decoding circuit for the second example, which we solved in this class. The first example for which we constructed standard array table is for 6,3. In example 2, we constructed standard array table for 7,4 linear block code. So this standard array table is for 7,4 linear block code. So now how these error patterns are written. Since n value is 7, we will have 7 error patterns. First one is 111. So this represents S1. I have written it over S1. And then we have S2, S3. So 111 represents S1, S2, S3. Min term concept is applied. 1 means A, 0 means A bar. This is the min term concept. So 110 is written as S1, S2, S3 bar. 101 is written as S1, S2 bar, S3. Similarly, 011 is written as S1 bar, S2, S3. Similarly, 000 is written as S1 bar, S2 bar, S3 bar. So this syndrome column is represented using an expression based on min term concept. So now how to construct the decoding circuit for 7,4 linear block code. So in order to decode the error, we need to compute syndrome. So syndrome S is nothing but R into H transpose. For 7,4 linear block code, we had computed H transpose. How did we compute H transpose? Parity followed by identity. So parity followed by identity is nothing but H transpose. Same H transpose is substituted here. Multiply it with received vector. N value is 7. Therefore, received vector is of 7 bit. So R1 to R7. Multiply R matrix with H transpose. If you recall, we had solved such examples in the previous classes. Multiply R matrix with H transpose. And how this R matrix is written? N value is 7, so R matrix will have 7 elements, R1 to R7. Multiply this with first column. R1 is 1, R2 is 1, R3 is 1, R5 is 1. Second column, R1 is 1, R2 is 1, R4 is 1, R6 is 1. Similarly, last column, R1 is 1, R3 1, R4 1, R7 1. So these are the syndrome bits we have obtained by multiplying R into H transpose. So now we can construct the decoding circuit. Received vector has 7 bits. So 7-bit shift register R1 to R7. Through this shift register, the received vector will be fed. We have 3 syndrome bits S1, S2, S3. Based on the equation of S1, S2, S3, make the required connections for modulo 2 adder. 3 modulo adders because 3 syndrome bits S1, S2, S3. The input for S1 are R1, R2, R3, R5. Similarly, the inputs for S3 are R1, R3, R4, R7. Using these syndrome equations, make the necessary connections for these modulo adders. So which will generate S1, S2, S3. So till here, this is nothing but syndrome calculation circuit, which we had solved in the previous class numericals. So syndrome calculation circuit is followed by error detection and correction. So if you observe this error bits, we have true variable S1 as well as complemented S1 bar. Similarly, we have S2, S2 bar, we have S3, S3 bar. So 3 NOT gates. First NOT gate generates S1 bar, next one generates S2 bar and S3 bar. So what is E1, S1, S2, S3? So connect S1, connect S2, connect S3. It is like a logic diagram which will generate E1. What is E3? E3 is S1, S2 bar, S3. Connect S1, connect S2 bar and connect S3. Similarly, what is E7? E7 is S1 bar, S2 bar, S3 bar. Using these error equations, make the necessary connections and all the terms are ANDed, so AND gate. And how these error equations are written? Using this syndrome column. Using this syndrome column. If it is 1, represent true variable. If it is 0, represent complemented variable. That is min-term concept. Using syndrome column, all these error bits are written. And these error bits are used to construct decoding circuit. So E6 is S1 bar, S2, S3 bar. E6 is S1 bar, S2, S3 bar. So once you make all the error pattern connections, these error plus the received bit will generate the corrected bit in code vector. E1 plus R1 will generate C1. The second error pattern plus the second received bit will generate corrected bit C2. Similarly, error bit E7, received vector 7th bit will generate the corrected bit C7. Add the error bit with the received vector, which will give us the corrected code vector. So we know that n value is 7. You can observe the output is also 7-bit. So 7-bit code vector. And this corrected code vector is generated by performing XOR of error bit with the received bit. Perform XOR or modulo 2 arithmetic addition of error bit and received bit, which will generate the corrected code vector bit. So this is how the corrected sequence is generated using the decoding circuit. So this circuit, we call it as error correcting circuit. And the given linear block code is 7,4 linear block code. By referring standard array table, determine the expressions for error bits. Using the expression, make the necessary connections for AND gate. Use XOR, and the input to XOR gate is error bit and the received bit, which will generate the corrected code bit. So this is how this circuit can be utilized in order to decode the error, and we can perform the error correction. So in this class, we have understood how to construct the standard array table and how this standard array table can be utilized in order to detect a transmission error in the received vector, and how to draw the decoding circuit by using this standard array table. Using the standard array table, write down the error bit expressions and then draw the decoding circuit. So in the next class, we'll start with the second half of module 3, that is the cyclic codes. Thank you.